In this video, we're going to talk about 9.2, series and convergence. So our objectives are to understand the definition of a convergent infinite series. Then we're going to use the properties of infinite geometric series. This is one of the types of series that we can not only tell you if it converges, but what it converges to. The other type that we can do that with is to use properties of infinite telescoping series. So these two are important because if you get them on a test, you're going to see instructions that are going to tell you to tell what the series converges to. That should be a hint that it's one of these two types of series. And then use the nth term test for divergence of an infinite series. So let's go ahead and talk about some things here. Actually, let me just point out that this is a test for divergence here of an infinite series. So never, ever, ever, actually, let me make this a little later here. There, so you can see that a little better. So never, ever, ever, ever try to conclude convergence by the nth term test. Okay, so already going to tell you that's a big pitfall, so don't do that. So an infinite series is the sum of the members of an infinite sequence. Just as we define integrals over infinite domains, we have to be careful in defining what it means to add an infinite list of terms. So suppose the sequence a sub n is defined from n equals 1 to infinity, is an infinite sequence, then the sum of the first capital N terms of the sequence is called the partial sum of the sequence, where S sub n is equal to, and we should make this match with that. If we're going to use a capital N over there, we need to use a capital N over here. So the nth partial sum starts with A1, adds A2, A3, all the way to A capital N. And we can use sigma notation for that as k equals 1 to capital N of A sub k. That's the nth partial sum. So let's find S sub 5 for the sequence n from n equals 1 to infinity. S sub 5 will be 1 plus 2 plus 3 plus 4 plus 5. When we add them all together, that'll be 15. 3, 6, 10, 15. So 15 will be the fifth partial sum. Notice we increase n, forming partial sums, S1, S2, dot, 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 Sn. We define a sequence of partial sums, Sn, and this is going to be n equals 1 to infinity, is what that's going to be defined on. So for a convergent series, for the infinite series, a sub n equals 1 to infinity, the nth partial sum is S sub n equals A1 plus A2 plus dot, 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 plus AN. And big idea here, red star right there, if the sequence of partial sums, Sn, so to infinity, converges to S, when I take that limit as n goes to infinity there, if it converges to S, then the series of the series an of n equals 1 to infinity also converges. The limit s here is called the sum of the series. So s is a1 plus a2 plus dot 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 plus an plus dot 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 dot, and that would be equal to saying s is equal to the summation n equals 1 to infinity of an. This is the Greek letter S, capital S in Greek, and that's how these two things are related, is this is summation notation, sigma notation, and that capital letter S in Greek is standing in place of this capital letter S right here for the summation of that series. So if the sequence S of n equals 1 to infinity, diverges, then the series diverges. Let's look at an example here of 1/2, 1/4, 1/8, dot, 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 1 over 2 to the n. So we have a sequence here, 1 over 2 to the n equals 1 to infinity is really what we have there for our closed form. Let's just go ahead here and look though at the partial sums. S1 equals 1/2. S2 equals 1/2 plus 1/4 is equal to 3/4. S3 is equal to 3/4 plus 1/8 is equal to 7/8. S4 is equal to 7/8 plus 1/16 is equal to 15/16. Dot, 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 dot. So we're going to take a look at this and say that Sn appears to be 2 to the n minus 1 over 2 to the n. So the limit of n goes to infinity of 2 to the n minus 1 over 2 to the n is going to be limit as n goes to infinity of 2 to the n over 2 to the n minus the limit as n goes to infinity of 1 over 2 to the n. This is going to be 1 minus, that's going to go to 0, is 1. Thus, the series converges to 1. But we must be cautious, so consider the series n equals 1 to infinity of 1/2 plus 1 over n. So if we look at this, S1 is going to be 1/2 plus 1 over 1 is 1/2 plus 1 is 3/2. And then S2 is going to be equal to 1/2. It's going to be that 3/2 plus 1/2 plus 1 over 2. So that's going to be 2 plus 1/2 is 5/2. And then S3 is 5/2 plus 1/2 plus 1/3 is going to be 3 plus 1/3 is going to be 10/3. So that's 1.5, 2.5, 3.3 repeating. S3 4. It's going to be 10/3 plus a half plus a fourth. And that's going to be 23. Let's see. So this is going to be 10/3 plus 3/4. 4 and 3 is 49/12, which is 4, and a 12th is equal to 4.083, repeating like that. All right, so do we see a pattern here? So it looks like this is just blowing up. So this series is divergent. We know that Sn is always going to be bigger than n/2, because limit as n goes to infinity of 1/2 plus 1/n is going to be 1/2. Limit as n goes to infinity, n/2 goes to infinity. So this series diverges. You don't believe me? Just look. This is bigger than 1/2. This is bigger than 1. This is bigger than 3/2. This is bigger than 2, and so on. And I can say this is bigger than n/2. So that's always the case. And so this is greater than something that's going to infinity. It also has to go to infinity. We're going to do that with something called a limit comparison test later in this chapter, more formally. But I just see the pattern here that this is getting bigger and bigger and bigger and not getting closer and closer to anything. Like this was getting closer and closer and closer to 1. This is not getting closer and closer and closer to anything. So important. And one of the things here that we're going to see with the nth term test right here is that this limit of the nth term did not equal 0. So that's going to tell me right away that the series is going to diverge. More on that later, though. So important note, very few types of series can we just sum and determine convergence. We'll develop methods and tests to do so in the near future. But one of the special types of series that we can tell whether it's going to be convergent or not and tell you what it converges to is going to be a geometric series, where we are going to be multiplying by a common ratio that we call R. So the series A1 plus A2 plus ... plus AN is geometric if the ratio of consecutive terms A sub n plus 1 divided by A sub n is always equal to some number R. R is called the common ratio. So the test for convergence of a geometric series with ratio R diverges when the absolute value of R is greater than or equal to 1, and converges if the absolute value of R is less than 1. If the series converges, then we have the formula here that it converges to A over 1 minus R. If it was written in the form of n equals 0 to infinity, A R to the n, like that. Notice that this is indexed at 0. Told you sometimes it would be good for us to index at 0. Sometimes it would be better for us to index at 1. This is one of those cases where we want to index at 0. So the first term in the sequence here is going to be a, or a sub 0 right there is going to be that right there. I might actually put a sub 0 right there, like that. And if this is not written that way, if it starts at 1, then we're going to have to maybe think about what's its first term, what's its common ratio, and use the formula that way. All right, let's consider the geometric series of 3 over 2 to the n. N equals 0 to infinity. So algebraically, 3 over 2 to the n is going to be the same thing as 3 times 1 over 2 to the n, which is equal to 3 times 1/2 to the n. So we have an a naught here, and we have an r here. Because r is equal to, because 1/2 is between -1 and 1, we're good. The series will converge. It's going to be equal to 3 over 1 minus 1/2 is 3 over 1/2 is 6. Converges. All right, let's consider now 3/2 to the n. 3/2 is bigger than 1, so the series diverges. Don't even need to think about that. That's geometric, where my first term was a0 is 1 here, and r is equal to 3 over 2. So it's pretty rare, actually, to be able to tell what the series converges to. Geometric series are one of the few examples of series that can be summed with a formula like that. The other example is going to be telescoping, which we'll get to in a second. But first, let's look at 1 minus 4/5 plus 16 over 25 minus 64 over 125 plus dot, 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 plus -1 to the n minus 1 of 4 to the n minus 1, 5 to the n minus 1. Let's go out one more term here and say that this is -1 to the n times 4 to the n over 5 to the n. If we would just carry that out one more, so that's going to be a n is equal to -1 to the n times 4/5 to the n, like that. So we have a series here of -1 to the n, 4/5 to the n is a n equals 0 to infinity, n equals 0 to infinity. This is a -4/5 to the n. There's a 1 there. My a sub 0 is 1. My r is -4/5. And -4/5 is between -1 and 1. So the series is going to converge. So yes, it's geometric. And what is the sum? Well, since A0 equals 1 and R equals -4/5, S is going to be equal to 1 over 1 minus -4/5, because it equals A naught over 1 minus R. It's going to be 1 over 1 plus 4/5. S is going to be equal to 1 over 5/5 plus 4/5 is 1 over 9/5 is equal to 5/9. 1 over something is the reciprocal of that something. So that's what my sum is. Is 1 over n squared geometric? N equals 1 to infinity. No. Because we're not multiplying by a common ratio. I'll go ahead and show you the terms here. That this is 1 over 1 is 1. S1 equals S2 is going to be 1 plus a quarter is 3/4. S3 is going to be, actually, let me just find the, so I have 1 plus a quarter plus a ninth, and each time I'm not multiplying by a common ratio here to get the next addend. 16, so no. 1/4 over 1 equals 1/4. 1/9 divided by 1/4 is 4/9, and they're not equal, so not geometric. This is going to be another type of series that we're going to learn how to deal with some other time later in chapter 9. Next thing that we're going to talk about in this section is a telescoping series. So this is another type of series that you'll actually be asked to sum. Telescoping series has the form of B1 minus B2 plus B2 minus B3 plus B3 minus B4, dot, dot, dot. And these zero each other out along here. And you're left with B1 minus B n, or B1 minus, should be a minus right here, minus Bn plus 1. So fix that in red here. That needs to be a minus sign there, as the pattern is term minus term, so on. So we would have Sn is B1 minus Bn plus 1 when all the other things go away. So there's a lot of fortunate cancellations in the middle. We're not always necessarily left with one term on the left and one term on the right. You could be left with 2 terms on the left and 2 terms on the right, or 3 terms on the left and 3 terms on the right. But there's got to be the same number of terms on the left with terms on the right, the same number of positive terms and negative terms when we're done. And this has to do with partial fraction decomposition lots of times. So consider the telescoping series summation from n equals 2 to infinity of 1 over n squared minus n. And what is the sum? So we're going to look at 1 over n squared minus n and try and decompose that. That's 1 over n times n minus 1, which is going to be a1 over n plus a2 over n minus 1. So we're going to have a1 times n minus 1 plus a2n needs to be equal to 1. So a1 plus a2, the n parts, need to be equal to 0 since this is 0n plus 1. And negative a1 is equal to 1. So a1 is going to be a negative 1. If a1 is negative 1 plus a2 is equal to 0, a2 is equal to 1. So that means that we have a negative 1 over n plus 1 over n minus 1. I'll write it this way, 1 over n minus 1 minus 1 over n, like that, is what this is going to be equal to. So that means that I have, for n equals 2 and above, my series n equals 2 to infinity of 1 over n squared plus n is equal to 1 over 2 minus 1 minus 1 over 2 plus 1 over 3 minus 1 minus 1 over 3 plus 1 over 4 minus 1 minus 1 over 4 plus dot 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 plus 1 over n minus 1 minus 1 over n. So this is going to be equal to 1 minus a half plus a half minus a third plus a third minus a fourth plus dot 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 plus 1 over n minus 1 minus 1 over n. And this zeros and that zeros, and that'll zero with a 1 over 4 that's there. And this will zero with a negative 1 over n minus 1 that's there. Now I'm going to get that this s is going to be equal to the limit as n goes to infinity of 1 minus 1 over n. And so that's going to be equal to 1 minus 0 is equal to 1. I can tell you that it converges, and I can also tell you what it converges to. Converges to 1. All right, let's look at some properties of infinite series. So if the series a sub n and the series b sub n are convergent series, capital A, capital B, and capital C be real numbers, such that the series a sub n converges to A, the series b sub n converges to B, then the following series converge to the indicated sums. This is lowercase c, so the series lowercase c, that constant multiple, times a sub n is going to be equal to c times a. The series a sub n plus b sub n is going to be equal to a plus b. And the series a sub n minus b sub n is going to be equal to a minus b. These rules follow straight from limits because you remember that the sum of the series is the limit as n goes to infinity of the sequence of the partial sums. And so we're going to inherit those limits from sequences and limits that we had before with constant multiples and sum difference rules as well. All right, so this is going to be our first actual test that we will try this test first, always. Unless you know otherwise, always try this test first here. So this is number 1 on our sheet of tests for a reason, even though we learned about the other tests, geometric and telescoping, before we talked about this one. Always do this one first. And again, never, ever, ever never conclude convergence from this test. Only ever divergence. All right, I think I've said that a couple times now. Hope that that's enough times. Maybe I'll say it again later so you get it in your head that this is the nth term test for divergence, right? So theorem 9.8, the limit of the nth term test of a convergent series, if the series of a sub n as n equals 1 to infinity converges, then the limit as n goes to infinity of a sub n has to equal 0. We usually talk about this way with theorem 9.9 is really the test that we're going to use. So it's a corollary. It's the same thing. So knowing that the limit as n goes to infinity of a sub n equals 0 is not enough to conclude that the series converges. It's necessary but not sufficient, I think is the way to say that with logic. So it's one of the conditions that has to be met, but not the only condition that has to be met. So we will make use of the contrapositive of theorem 9.8, if you know that word from logic, to test for divergence. So we have this kind of thing in logic that says if P happens, then Q has to happen. And we can say that if Q doesn't happen, then P definitely didn't happen. So if it was convergent, then the limit went to 0. But we can say if the limit doesn't go to 0, then it's definitely not convergent. So we can only conclude that it's not convergent. We can't conclude that it is convergent. So if the limit of a sub n as n goes to infinity is not 0, then we know that the series of a sub n as n equals 1 to infinity diverges. That's going to be our most important test for convergence and divergence. To start off with, it's going to be number 1. Just try that. That's super easy. So let's go ahead and let's think about this one. Consider n goes to infinity. Limit n goes to infinity of cosine n. And we say that equals, I don't know, but it definitely doesn't have to equal 0, right? It could be anywhere between the interval. It's somewhere in the interval of -1 to 1, but we don't know where it is. Thus, the series diverges by the nth term test, because it doesn't always all the time equal 0. If we're going to add infinitely many things, we have to keep adding 0 at the end so we don't change what it is that we're adding up to. That's the only way it works. Let me just say this one more time because it's really important. Never, ever, ever write the series converges by the nth term test. Never, ever, ever, ever write that. It's wrong. Okay? It's a good way to lose points on your test. Never write that. All right, now let's think about n factorial over 2n factorial plus 1. I think that 2n factorial, yeah, is supposed to have parentheses around it. It's not. It's supposed to be like this. So that was not 2 times n factorial, that's 2n factorial. So, nope, actually it was 2 times n factorial. So note here the difference between them, that 2 times n factorial is not the same thing as 2n factorial. 2 times n factorial is going to be 2 times n minus 1 times dot 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 times 3 times 2 times 1. And you're just going to be multiplying by 2 there each time. 2n factorial is equal to 2n times 2n minus 1 times 2n minus 2 times dot 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 times 3 times 2 times 1, like that. Not the same thing, all right? So recall, in general, that n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 times dot 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 times 3 times 2 times 1, like that. So we need to think about this nth term test here. Limit as n goes to infinity of n factorial over 2 times n factorial plus 1. The easiest way for me to do this is to just multiply by 1 over n factorial, top and bottom, and to get the limit as n goes to infinity of 1 over 2 plus 1 over n factorial, like that, which is going to be equal to 1 over 2 plus 0 is 1/2, which is not equal to 0. So this series diverges by the nth term test. Now let's look at, we dealt with this one before. Limit as n goes to infinity of 1/2 plus 1 over n. And this is 1/2 plus 0 is 1/2, which is not equal to 0. So this diverges by the nth term test. All right, let's think about 1 over n. Does the series diverge? Limit as n equals, or as n goes to infinity of 1 over n equals 0. So it fails the nth term test for divergence. Divergence. And we're going to need to try another test. We already know from earlier that it's going to converge because we actually did that with partial sums earlier, but we'll have another test later on for P series. Actually, excuse me, that one diverges. We did that one earlier. And we'll have some different tests that we can use. We can either use the interval test or the P series test, and that one's going to diverge. So evaluate, find the sum of the following here. So first things first is let's identify what type of series this is. So we see that this starts at n equals 1. We're going to want to maybe plug in and start seeing what this does and rewrite it. So this is -2 to the 0 over 5 to the second plus -2 to the first over 5 to the third plus -2 to the second over 5 to the fourth plus dot, 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 dot. So it looks like my A0 here, my first term, is 1 over 25. And it looks like my R is going to be a -2 over 5 that I'm multiplying by -2 in the top, and I'm multiplying by 5 in the bottom. And since the absolute value of R is less than 1, converges. So I'm going to rewrite this as the same thing as n equals 0 to infinity of 1 over 25 times -2/5 to the n. And we have 1 over 25, so 1 minus a -2/5 is going to be equal to 1 over 25. 1 plus 2/5 is 1 over 25 over 7/5. So I'm going to multiply by 25 over 25 to clear the fractions. And that's a 1 over 7 times 5 is 1 over 35 for what my S is here. All right, that was my last one for this video. And we'll come back next time and talk about the integrals test and the P-series test. See you for the next video.